Hi, welcome to Data Nutshell. Now that we have explored RAID 2 and seen how it uses bit level stripping with Hamming code parity, let's move on to the next RAID level, that is RAID 3. This one is a little more practical than RAID 2 because it was actually used in some storage systems. To understand it well, we'll look at how RAID 3 stores data, what role the parity disk plays, the performance characteristics, when it's good, when it's bad, and why RAID 3 eventually fell out of favor and is not used in today's systems. So, how RAID 3 works? RAID 3 uses something called byte level stripping. That is, data is split across disks byte wise, and it has a dedicated parity disk. So, if you have three disks for data, you will have one extra disk for parity. Let's break that down step by step. Imagine you have multiple disks in an array, say disk 1, disk 2, disk 3, and you have one disk for parity, say disk P. When data comes in, instead of writing a whole block to one disk, RAID 3 splits at different bytes across all the data disks. So, say for example, if you are storing a file, the first byte of that file will go to disk 1, the second byte of that file will go to disk 2, the third byte will go to disk 3, and the fourth byte will go to again disk 1. This continues in round robin. So the data is getting stripped at byte level across the disks. But that alone isn't safe because what if one disk fails? That's where the parity disk comes in. What's the role of the parity disk? Because alongside the data disks, RAID 3 has one dedicated disk just for storing parity information. We know what parity is. Parity is a kind of checksum. It's some extra piece of information that lets you rebuild the lost data if one disk fails. So the way it works is simple. For each set of bytes you are writing across the data disk, say you write byte 1 to disk 1 and byte 2 to disk 2 and byte 3 to disk 3, for these byte 1, byte 2, byte 3, you will calculate a checksum and you will write it to disk P. So this parity is usually the XOR of those bytes. Say byte 1 XOR byte B XOR byte C. This equals the byte value that you will write to the parity disk. That's the parity byte corresponding to those three data bytes. Suppose you have byte 1 to disk 1, byte B to disk 2, byte C to disk 3. The XOR of A, B, C will be P, and this P will go to the parity disk. Now, if say disk 2 fails and you lose byte B, you can rebuild it using XOR of A, C, and P. So, A XOR C XOR P will give you that lost byte B. This way, RAID 3 can survive the failure of any single disk. So, RAID 3 allows you one disk failure. Let's see the performance characteristics of RAID 3. What are the strengths? The strength of RAID 3 is very high throughput. RAID 3 can deliver very high throughput for large sequential reads and writes. Why? Because when reading a large file, all the disks work together in parallel and each disk contributes a part of the data. So you get very fast transfer rates. This made RAID 3 attractive for workloads like video streaming, scientific computing, where large files are written or read in sequence. What's the weakness? The weakness is it struggles with small random reads or writes. Why? Because data is stripped at byte level. Any read or write you do, even for a single byte, involves all disks working together. So for smaller files, it becomes inefficient. You can't just pull one small chunk. You will always have to involve that entire array of disks you are using. The dedicated parity disk is also a bottleneck for write operations because if you write 3 bytes to those data disks, you will have to do one calculation or to calculate the checksum of those 3 bytes and then write that parity byte you get to the parity disk. So that becomes a mathematical bottleneck. And why RAID 3 fell out of favor? Because RAID 3 was used in some specialized systems. Now it's rarely used. Why? Because the byte level stripping means poor performance for small workloads. The dedicated parity disk creates a single bottleneck for heavy write operations because all the parity writes are happening to the same parity disk. Later, when we see RAID 5, RAID 6, we see this design is improved by using distributed parity. That is, parity bytes are written across multiple disks. So it gives more balanced performance and more reliability. So while RAID 3 was better than RAID 2, it was still just an intermediate design, but the more practical RAID levels we are yet to see with RAID 5, RAID 6, and subsequent levels, which we will look into in our next videos.